We've spent considerable time understanding our data, cleaning it, and extracting meaningful features. But the journey doesn't end there. Once our data is prepped, the crucial next step is to validate the models we build, ensuring they truly learn from the patterns and don't just memorize the noise. This transition from data understanding to robust model validation is where statistical inference and resampling techniques become indispensable. The goal of any machine learning model is to perform well on unseen data, a concept we call generalization. Simply splitting our data once and reporting an accuracy score often isn't enough. Such a single snapshot can be misleading, susceptible to the particular data points in that specific test set, potentially overestimating or underestimating our model's true performance. We need methods that provide a more reliable and less biased assessment. Statistical inference provides the foundational framework for drawing conclusions about a larger population based on a smaller, representative sample. In machine learning, this means making informed decisions about our model's performance on future data, based on its behavior on our available dataset. It allows us to move beyond descriptive statistics and make statements about uncertainty and confidence. One powerful application of statistical inference in ML is hypothesis testing, especially for feature selection. Imagine you have several potential features, and you want to determine if a specific feature genuinely contributes predictive power or if its apparent utility is just due to random chance. By formulating a null hypothesis, that the feature has no significant impact, and testing it, we can statistically ascertain its importance, leading to more parsimonious and effective models. Hypothesis testing extends further to comparing entire models. In A/B testing scenarios for machine learning, we might want to compare the performance of two different model architectures, two sets of hyperparameters, or a new model against an old one. By setting up hypotheses about their performance metrics, such as accuracy or F1 score, we can use statistical tests to determine if any observed differences are statistically significant or merely random fluctuations. Beyond point estimates for predictions, understanding the uncertainty inherent in our models is vital. Confidence intervals for predictions provide a range within which the true outcome is likely to fall, with a specified level of confidence. This is incredibly valuable in critical applications where knowing how sure the model is about its prediction is as important as the prediction itself. Similarly, confidence intervals can be estimated for model parameters. These intervals give us a sense of the stability and reliability of the coefficients in a linear model, for instance, or the estimated probabilities in a logistic regression. A wide confidence interval might suggest that our parameter estimate is highly sensitive to the specific training data, indicating potential instability. However, the efficacy of traditional statistical inference often hinges on assumptions about data distribution or requires large sample sizes. This is where resampling techniques come into play, offering robust, distribution-free ways to estimate statistics and assess model stability, especially when data is scarce or nonparametric methods are preferred. Bootstrapping is a powerful resampling method that involves repeatedly drawing samples with replacement from our original dataset. For each bootstrap sample, we train our model and estimate a performance metric, or a parameter. By repeating this process hundreds or thousands of times, we generate an empirical distribution of our statistic, allowing us to estimate its variance, biases, and construct confidence intervals without strong distributional assumptions. Another cornerstone of robust model evaluation is cross-validation. Techniques like k-fold cross-validation divide the data into k equally sized folds. The model is trained k times. Each time, one fold is used as the validation set and the remaining k1 folds for training. This ensures that every data point serves as both training and validation data, providing a more stable and less biased estimate of the model's generalization performance. It's also critical for hyperparameter tuning. Ultimately, statistical inference and resampling techniques are our strongest allies in the fight against overfitting and in ensuring strong generalization. By quantifying uncertainty through confidence intervals, rigorously comparing models with hypothesis tests, and getting robust performance estimates via bootstrapping and cross-validation, we can identify when a model is merely memorizing training data versus truly learning underlying patterns. In conclusion, Moving from data understanding to robust model validation is a critical pivot in any machine learning workflow. By embracing statistical inference, hypothesis testing for feature selection and model comparison, understanding confidence intervals for predictions and parameters, and leveraging the power of resampling techniques like bootstrapping and cross-validation, we empower ourselves to build, evaluate, and select models that are not only high-performing but also reliable and generalize well to the complexities of real-world data.